Thanks for the opportunity to talk today. There's going to be a slight segue. I'm not only working on hydrogenases, I must admit, considering the audience, I must say that up front. I'm also working on formate dehydrogenases, and also carbonic anhydrase will feature heavily here. So hopefully you won't judge me too hard for that. So I'm going to talk today about using enzymes to understand and control the local environment of catalysis. And hopefully over the next 20 minutes, what I can do is show you that some things you probably already know, that enzymes are really good model catalysts, and by using them as models, we can start to understand some properties of catalysis that maybe we can't without having our dream model catalyst already in existence. So in particular, if my screen's going to switch, it is, woohoo, I'm interested in electric catalysis for fuel production. So to give you the kind of block diagram scheme of what I'm interested in having electrodes with catalysts immobilized on them. In the context of this can definitely be an enzyme, taking renewable energy and using the catalyst to convert a feedstock to a fuel. And this segues really nicely from Carol's talk, which I'm very gracious for, in that lots of people work on the catalyst while we're all asking this question of how do we improve fuel production. But my interest actually more lies in the rest of the system, the other parts of the system. So how do we deal with getting our feedstock and our fuel in and out in the best way possible? And how do we make our catalyst sit in a local environment where it can perform at its best? Because we spent all this time developing catalysts, we want them to operate at their best. So I'm going to talk a lot about local environments, and these are something that's pretty much unavoidable when you're doing electric catalysis, because inherently we want to do some chemistry. By doing some chemistry, we inherently change our species at our surface or within our electrode. By doing that, it's going to modify the properties, and we need to consider what's really happening in that local environment. So why enzymes? Why am I here talking to you at a hydrogenase lecture today? Well, it's because enzymes are really good model catalysts. So obviously these are properties all you guys know already, but they've got really high selectivity, so we can pretty much do one reaction and one reaction alone. They display Michaelis-Menten kinetics, unlike the high affinity, with a high affinity, unlike first order kinetics for heterogeneous systems. They also give us the opportunity to control our rates of different reactions by varying enzyme loading. So unlike our heterogeneous surface that has an inherent rate, we can control our loading of enzyme on the surface to control what reactions we have and what rates they are progressing with. And also, as I'm sure people here can tell me much better than I can tell you, they have really solution dependent, really pH dependent properties, which is something that's really fascinating due to their kind of optimized structures. And in the spirit of making more fuel, there's been a lot of interest recently, well, recently in the last 10, 15 years, in particular in immobilizing enzymes in porous electrodes. And there's been some great reviews on this, so I won't go into too much detail. But when you put an enzyme into a porous electrode, there are a huge amount of advantages that are claimed to occur because of that. In particular, just more enzyme can be loaded. If we can put more enzyme in theory, we can make more fuel. Makes sense, right? But there's also properties about whether enzymes are more stable in a porous electrode. Can we prevent denaturation and reconformation? Can we improve how they're wired to the surface for direct electron transfer? And everything I'm going to show today is direct electron transfer. No mediators involved here. The other thing is something that's even more in the last few years come out, which is the idea of nano-confinement. So Fraser Armstrong at Oxford has talked a lot about this. The idea of when we immobilize enzymes within a porous electrode, can we get different environments and properties from their immobilization within that structure? Because we inherently move from 3D diffusion to a flat surface to 1D diffusion down some tortuous pores. And this allows us the opportunity to think about creating a local environment that can maybe make intermediate transfer better, help with cofactor recycling. And there are a number of reasons that you might think this is beneficial. But enzyme people aren't the first people to get there. There's been a lot of work in heterogeneous catalysis also on local environments. And they also approach this from a similar kind of thought of, well, if we can make an environment confined, how can we use that to benefit the performance of our system? In particular, gold, copper, silver for CO2 reduction. And this kind of interest stems from what is inherently a poor catalyst. Heterogeneous catalysts aren't selective. They aren't going to do CO2 reduction selectively. They're always going to make hydrogen alongside this. And therefore, what's been found is when you put them into a porous electrode, you effectively suppress your side reaction, your hydrogen evolution, by making the local environment really basic. So moving your local pH to be much higher. This suppresses hydrogen, maybe hurts your CO2 reduction a little, but overall net benefit because your Faradaic efficiency goes through the roof, relatively speaking. Therefore, what we're doing really is we're compromising the performance of our system because they're inherently poor catalysts, which is not really the case with enzymes. So it's interesting to consider, how do we start to rationalize the difference between these heterogeneous systems and our dream model enzyme system? Well, if we're talking about local environments, we definitely need to understand what's happening in the local environment. We can't just say, well, it's probably fine. We want to understand that local environment. So what do we actually know about the local solution environment? Well, unfortunately, the answer from sort of standard electrochemical experiments is not a lot. We know what the system is at time zero because we made it. We've got a solution of a known pH, reactance buffers. We understand all this because we put them there. Then we turn our current on and we start doing an experiment, and we lose all our information about what's happening locally because we start doing a reaction and driving local environments. So therefore, our only metric as we go through the experiment pretty much is current. You can do some spectroelectrochemistry on very simple flat surfaces, but in a big complex porous system, slightly beyond our scope to really understand with good resolution what's actually happening at that surface. The only thing we have is kind of bulk measurements at the end. So how do I do a talk about local environments if we can't understand them? So my answer to this, and there are other answers to this, but the one I'm going to talk about today, is finite element modeling. The concept of using computational modeling to basically solve a mathematical model of our system over discrete cells or finite elements. And what this allows us to do is take physics we understand the kinetics of an enzyme on a surface, we understand reaction diffusion, we understand mass transport, and then we can link them all together and apply them over a complex geometry such as our porous electrode. And by doing this, it allows us to kind of fill in the gaps of the things. From what we do know, we can start to use modeling to fill in the gaps of what we don't know. And as long as our physics is sound, which fortunately it often is, we don't break physics too often, we can kind of start to fill in these gaps and interrogate what's happening in the model and correlate that to our experiment. It's worth saying this isn't DFT. We're not working from first principles. Everything has to be describable with some kind of analytical expression. So your model is only as good as your analytical expression. But we can start to fill in some of these gaps. And what I'm going to show over the next few slides is a lot of simulation alongside experiment, and the two kind of intermingle, and we can show how we can link the two, and hopefully there's good correlation. But what this allows us to do is basically fill in the gaps, and this middle column is now populated, and hopefully we can understand our local environment a bit by using these physics we hopefully aren't going to debate too much about. So why do we care? Why is this useful? Well, if we can understand and model our local environment, we can then start to optimize it. And this is the first thing we did. What we did is we showed that by basically taking a buffer system that's only changing in pH and a few composition components, we're adding in different buffers, MES, MOPS, to our bicarbonate buffer, we can drastically increase our electrocatalytic activity. So we go from our bicarbonate buffer at the top, add some MES in, current improves, add some MOPS in, current improves again. And these are good buffers, and this is kind of what this work shows. Effectively, by adding in better buffers, we can reduce our local pH change and make our local pH more optimal for the enzyme. And by doing this, we improve our current density. Great, woohoo, we're making better catalysts, we're making better catalysts perform better. But why is bicarbonate buffer so bad? And this was what the next thing we wanted to think about was, why, it's the simplest system, right? You take CO2, you purge it into some water, you have bicarbonate buffer. Can't avoid it. It's inherently present if you're trying to do CO2 reduction. Why does it perform so badly? And this stems back to CO2 hydration kinetics. And this is something that both can help and hinder, as we're going to show. When we purge CO2 into water, inherently it forms carbonic acid, which can then deprotonate to bicarbonate through to carbonate. And this is really slow, which is kind of fortunate in some cases, but also detrimental. But we have the prospect for CO2 to act as a buffer system to mitigate local pH changes and improve our local pH, and also act as a substrate for CO2 reduction. And inherently it's going to be doing both in a electrocatalytic system for CO2 reduction. And again, interested in enzymes, we were looking at how can we improve this and see how it affects our system. And the answer we came to is carbonic anhydrase, which is a fantastic enzyme, brilliant, amazing, really fast, catalytic rates through the roof. And this allows us to take our very slow catalytic reaction, and without adding any additional components to our solution, any mimics, anything like that, we just take our catalytic rate from being very slow to very fast. And it basically turns CO2 bicarbonate from being a really poor buffer into a really good buffer. So that works, that's cool, that might be interesting. We now need to see how that affects our system. So we went ahead and immobilized that into our electrodes. So everything I'm going to show is mesoporous ITO electrodes with some combination of enzymes immobilized. And you'll see this kind of scheme with different enzymes included as we go through to refer back to. And if we want to immobilize enzymes in ITO, the first thing we need to be able to do is prove we're immobilizing enzymes in ITO. Unfortunately, we can do this with QCM, so this allows us to show that we can co-immobilize these enzymes. I'm not going to dwell too much on this, but this gives us proof that we can actually load these enzymes quantitatively into our materials. And when we do this, we can actually start to study the effect of CO2 hydration. And we're going to start with hydrogenase, because what's really interesting about hydrogenase to me is its ability to do a in this project in particular, because it can do a reaction that does not use CO2 as a substrate. So in this system, CO2 is purely acting as a buffer. So therefore we can see, is it performing as a good buffer, because it's really sensitive to pH. And what we find is when we add carbonic anhydrase, our activity in bicarbonate buffer goes from 0.2 milliamp centimeter squared at our biggest overpotential to nearly 0.5. So that's a big increase just by immobilizing another enzyme. And you go, why is that? Is that sensible? We've not changed much, we've not changed our buffer. And you can then look at the local pH from the finite element modeling. And what you find is when you model in the carbonic anhydrase alongside, your local pH is reduced. We've basically made our bicarbonate perform like a better buffer, and actually to the point where it starts to perform like your MES or your other buffers that people often use with hydrogenase. MES is a brilliant analog of bicarbonate because it's got basically the same pKa, but no CO2 bicarbonate involved. And what we find is basically it's performing very similarly, and therefore just by increasing CO2 hydration, we can increase our hydrogen production. I.e., we've only changed our local environment, we've not changed our catalyst, but by changing the local environment, by increasing the kinetics of that buffer, we improve the activity. And then that leads really nicely into thinking about CO2 reduction, because now our CO2 has to act as a substrate and as a buffer, if we want it to act as a buffer. And you think, well, if it's our substrate, making it work as a buffer and converting CO2 to bicarbonate, well, that sounds like a horrendous idea, because we're going to take our CO2 away and turn it into bicarbonate, which is going to just hurt our activity. But what we actually find is if you look at the experiment, what you see is your formate production almost doubles, actually slightly over doubles. And this doesn't make sense, right? We're taking CO2 away. Why does that improve our activity? And this comes back to, again, from the model, we can look and say, well, this comes back to the properties of enzymes and their Michaelis-Menten kinetics. Well, if we can reduce our CO2 concentration locally, so these unfilled squares are without carbonic anhydrase, we can go to with carbonic anhydrase, our CO2 concentration does decrease. But it doesn't affect our activity of our enzyme because we have a really high affinity for CO2. Therefore, it doesn't matter that we've reduced our CO2 concentration, which is maybe counterintuitive, but when you think about how an enzyme performs, okay, yeah, I get it. And then you think about pH, and actually the pH dominates the activity. So we really need to work to optimize the pH over the CO2 concentration locally in these systems, because the CO2 concentration is not helping. But by accelerating these kinetics and making it perform as a better buffer, our local pH becomes better for the enzyme, and therefore we see better performance. So this is something that is inherently, because it is an enzyme and inherently because it's selective, we don't have to worry about hydrogen evolution. We just have to worry about the CO2 reduction, and the enzyme doesn't care about our substrate. But then we can controllably add back in hydrogen evolution. We can make our system deliberately non-selective by adding back in hydrogenase. And now, if we take hydrogenase and co-immobilize it with formate dehydrogenase, and then put in carbonic anhydrase as well, we can think, well, this is an enzymatic mimic, or approaching an enzymatic mimic of heterogeneous catalysis, but we still have our Michaelis-Menten kinetics. We've not gone to the low affinity first order kinetics of CO2 reduction. And what this shows is we see our hydrogen increase. Okay, that makes sense. We've got a lower local pH. Our hydrogen is going to increase, but also our CO2 reduction increases. This is unlike heterogeneous systems. And this leads to a very small increase in, or decrease in, the Faradaic efficiency for formate. But it can all be explained by the model again. And this is almost artificial in the sense that this comes just purely from the fact that we have these particular pH dependencies of the enzyme. CO2 concentration is unimportant. All we're doing is basically changing our pH activity to make the enzymes perform better. And it just happens that hydrogenase performs slightly better in the more optimal local environment versus FDH. So that's the only reason our Faradaic efficiency is worse in these systems. If we had different enzymes with different pH dependencies, maybe this would be different, or in fact, I would wager it would be different. So we've now got a system where we've got Michaelis-Menten kinetics, but no selectivity. That's one step towards heterogeneous catalysis. So the next question is, how does that affect heterogeneous catalysis? Unfortunately, that's a question we asked, and I've got some data to show you on it. What happens when we add carbonic anhydrase to gold, which is a really good CO2 reduction catalyst, one of the sort of classic systems for CO2 reduction, is our carbon monoxide, our activity for producing carbon monoxide decreases drastically, and our hydrogen evolution increases significantly. Let's not say massively. And this hurts our Faradaic efficiency for this reaction by adding fast hydration kinetics in by using carbonic anhydrase. And why is that? Again, we can start to fill in some gaps from the model. Well, as has kind of been alluded to, this is a first order, this has first order kinetics, so it's really sensitive to CO2 concentration. And we have reduced our local CO2 concentration. And by doing that, it means we get less CO2 reduction. With that, we also have converted CO2 into bicarbonate, reducing the local pH, which hurts our hydrogen evolution. Even worse than that, bicarbonate is an excellent proton donor for hydrogen evolution. So we have just made our system immeasurably worse by accelerating our CO2 hydration kinetics, which is really contrary to what you see for enzyme kinetics. So we've got these kind of systems that we've got to link through them, but really by the properties of enzymes, we have very different performance when we think about CO2 hydration kinetics to what we have for a heterogeneous system. And this can kind of be compared and contrasted, and we can say as we move from our Michaelis-Menten kinetics with selectivity through to a first order system that's not selective, effectively we have different responses, and our CO2 reduction activity definitely increases when we've got Michaelis-Menten kinetics, but that's all due to pH rather than that, and we don't have to worry about hydrogen. But then in the other end of the case, CO2 reduction hurt hydrogen evolution increases, so it gets significantly worse. So hopefully I've given you a very quick whirlwind tour through the world of local environments that occurs within porous electrodes. And they really are key to the performance of these electrocatalytic systems. And I really love looking at this and working on this. And it really shows how all these systems really do respond very differently, which must be considered. And finite element modeling can really start to understand this. And while fast CO2 hydration kinetics are beneficial for our enzymatic systems, that maybe we can think of our dream next generation synthetic catalysts that we've got people working on and developing, and these might follow these same properties as we get there. It's not the case for heterogeneous systems right now, and maybe this is something we need to start to consider as we move to the next generation of catalysts. So I'll briefly acknowledge the people I've worked with, because Professor Owen Reisner, I work in his lab, and it's a brilliant lab to work in. I've got brilliant co-authors. This is not work I've done alone. I've got all these co-authors that have contributed. We get enzymes from Inês Pereira in Portugal, who makes all this possible, and also ERC and Leverhulme for funding. So thank you. Any questions?
Thank you so